Welcome back. Today we join an industrial forge building heavy marine infrastructure where massive steel is shaped by thousands of tons of hydraulic force. Minutes later, the raw billet is closed into a continuous loop. The die compresses the glowing joint, forcing the steel to fuse under immense pressure. This mechanical bond alone is not enough for the open ocean. A deep water quench rapidly drops the metal's temperature, locking its crystalline structure into a hardened state. The sudden thermal shock increases tensile strength, but it also leaves the steel inherently brittle. To relieve this internal stress, the links must undergo a controlled tempering phase, balancing hardness with flexibility. Marine classification societies demand rigorous verification before any chain touches a vessel. Magnetic particle inspection reveals microscopic surface fractures invisible to the naked eye. Each link receives a unique stamped identifier, permanently tying the physical hardware to its metallurgical pedigree. In the testing lab, destructive impact and tensile trials push sample units past their breaking point. These controlled failures generate critical data on force and displacement. By measuring exactly how a sacrificial link deforms, engineers guarantee the operational integrity of the entire batch. Once certified, the heavy chains are coated in industrial black paint to resist saltwater corrosion. The contrasting white links serve as depth markers for the ship's crew. forging marine shackles requires identical thermal discipline. Inside the furnace, cylindrical steel billets absorb ambient heat until they reach a uniform forging temperature. Precise temperature control prevents localized weak spots during shaping. Hours into the production run, the shaped shackles are pulled from the heat. Suspending them before the quench allows atmospheric oxygen to burn off residual scale. Submerging them rapidly in the dark fluid completes the hardening cycle. The securing hardware demands tight tolerances. A stationary lathe cuts precise threads into the heavy hexagonal nuts, ensuring a frictionless lock when deployed. Bare steel cannot survive marine environments, so the components undergo a galvanized finishing process. A thick layer of zinc provides sacrificial protection. Salt water will corrode the zinc coating before it can attack the structural steel beneath it. The final assembly pairs the glossy silver shackle body with a vibrant red bolt. This high-visibility finish allows deckhands to quickly confirm that the pin is fully seated and secure. The finished hardware is boxed for transport, ready to handle immense static loads. Transitioning to fluid control systems requires an entirely different manufacturing approach. Here, industrial valves begin as lightweight polystyrene foam. A CNC milling machine carves the master mold from a solid block of aluminum. Aluminum dissipates heat efficiently, making it ideal for the rapid cooling cycles of foam production. Inside the press, steam expansion forces the polystyrene beads to fill every complex cavity of the mold. The resulting white foam component is a perfect, full-scale replica of the future metal valve. This vanishing mold technique allows for highly intricate internal geometries that traditional sand casting cannot achieve. Once the molten iron consumes the foam mold and hardens, the rough casting requires precision refinement. The raw valve body is mounted on a lathe where a hardened cutting tool shaves away the coarse exterior. Creating a perfectly flat, smooth flange surface is critical. Any imperfection here will compromise the high-pressure gasket seal. A heavy drill press bores the bolt patterns into the thick flange, aligning them to strict industry standards. Workers manually assemble the heavy components, torquing down the fasteners to ensure structural rigidity. The completed valves are staged on pallets destined to control flow in massive pipeline networks. A similar casting logic applies to commercial cookware, though the finishing demands are vastly different. As the freshly cast iron pots exit the cooling line, mechanical scrapers separate the molding sand and loose metal flash. Both the fine sand and the jagged metal scraps are collected and recycled. Nothing goes to waste. Bare iron vessels are paired with their matching lids. The thick walls and heavy covers are designed to trap steam and distribute heat evenly across the cooking surface. Raw cast iron is prone to oxidation, requiring a durable, non-porous barrier. The pieces move along a continuous mesh conveyor into an automated spray booth, receiving a thick coat of liquid ceramic enamel. The vibrant red finish is more than aesthetic. It seals the iron core entirely. The coated cookware then enters a high-temperature industrial oven operating near 800 degrees Celsius. During this secondary sintering process, the liquid enamel vitrifies, melting into a smooth, glass-like shell that permanently bonds to the porous iron surface. The resulting ceramic layer is highly resistant to acidic foods and thermal shock. The finished pots cool as they exit the firing chamber, transforming raw scrap metal into heirloom-grade tools. The backbone of heavy infrastructure relies on continuous material flow. Massive 15-ton coils of raw steel are secured with heavy strapping and loaded onto the factory floor. These dense spools are the starting point for high-volume structural pipe fabrication. Unwinding a coil of this magnitude requires immense mechanical tension. The wide steel sheet is fed into a heavy-duty slitting line. Here, an array of hardened circular blades applies immense shear force, slicing the solid metal into multiple continuous narrow strips. Maintaining precise width during this cut is critical, as these specific dimensions dictate the final diameter of the resulting steel pipe. The speed of the automated rollers maximizes throughput while keeping the tension perfectly balanced. After forming and welding, the finished pipes are securely banded. In the end, raw energy and industrial precision operate as one system, transforming bulk material into the structures that build the world.